you very much. Actually, when I was invited to give a talk on this conference dedicated to the University of Jean-Michel Bismut, I realized there are several choices, and another appropriate choice, talk which will be appropriate, I gave last week on Arbeitstagung, dedicated to memory of Hirzebruch, about how to extract in the right way square root of a head genus. But I will not repeat myself, so several people came actually from Max Planck Institute. So it will be about something also related to things which Jean-Michel was doing many years, like relation probability theory and Kähler and complex geometry. So I'll explain the thinking. The simplest setup one can develop this theory is the following one. We have a smooth algebraic curve over complex numbers, which is smooth projective curve minus some finite set, which could be empty. And we consider a vector bundle with a flat connection on complex vector bundle with flat connection, which is the same as the representation of a fundamental group. And I make one important technical assumption that if you consider monodromy around each removed point, then you get operator whose eigenvalues have absolute value equal to 1. It could be not necessarily unitary operator, it could be unipotent operator. And for example, if you consider connection coming from algebraic geometry, if you consider cohomology of some varieties depending on a point on a curve in algebraic way, then the eigenvalues of monodromy are roots of 1. So things coming from algebraic geometry provides satisfies this condition. And the claim that this, with such situation, one can associate canonically n real numbers, where n is the rank of my local systems, which are called Lyapunov exponents. And they're ordered in decreasing order. So how to define this? Of course, this Lyapunov exponents in much different contexts in usual, but now I explain how to define them in this case. You should make several choices, and the result will not depend on these choices. First, you choose a Kähler metric, smooth Kähler metric on a curve with no restriction to behavior to cusps. The only constraint is its total area is 1, so you get probability measure on a curve. And then you also pick a norm on fibers depending on smooth way, and such that it bounded as at punctures in a most obvious way, because you trivialize, say, making some cut, and you say that things are bounded, and also pick some initial point, and then now start to make a random walk, because now we have a metric. You can have Brownian motion, and so you get point depending on parameter t, and for large t you get a holonomy matrix, which will be identify one fiber and another fiber. And because I have choose a Hermitian norm on each fiber, then for this operator I have singular values. I multiply this operator by Hermitian conjugates, take square root, and I get some positive real numbers. So I get positive real numbers, and the claim that their logarithms grow linearly with time. And with probability 1, if you consider this trajectory, you'll get such limits for this singular values. So this follows from the multiplicative ergodic theorem of Asyledius, this famous result from 65. Actually, I want to explain now how to one can. Here I will mention there are a couple of computer experiments related to this story, and I explain how we calculated these numbers in. Where is this? Okay, I see. How one can calculate these numbers with pretty good precision, something like 6, 7 digits. Not more, I think it's really because to get extra digit we need exponentially larger time. Yeah, so Yeah, so how one calculates these numbers? For example, if suppose it's curve and is defined over Q bar. That's I'll explain. It's very convenient for calculations. Why it's convenient? Because by Bayes' theorem, we can do the following. We can add, there exists a finite set, C prime in S and C, so that C minus C prime is a covering of CP1 minus 3 points. It's a finite covering. There are many choices of the C prime, so you can choose any of such coverings. And then you consider direct image of my local system. It will be a local system of higher rank on CP1. And then you get a representation of a subgroup gamma 02, free group with T generators acting on SL2Z. It will map to GL and D, where D is the degree of this covering. Okay. Now, calculation of Lyapunov exponents can be reduced to calculation Lyapunov exponents on the bottom curve. But now we can endow it with hyperbolic metric. So it will be upper half plane divided by this free group. So CP1 minus 3 points is upper half plane divided by this gamma 02. And or hyperbolic disk. And then the claim that instead of making random walk, one can consider geodesic flow. It will produce the same numbers. And the reason is very old idea of Dennis Sullivan that if you consider random walk on, let's say, on hyperbolic disk, so effectively it will lie essentially in more or less bounded distance from some ray. So you will choose a random direction of this ray and then follow the ray. So the deviation will be sufficiently small, and then you'll get the same asymptotic behavior. Okay, so you get this, and how to produce, and now to work with geodesic flow, it's much easier because essentially you follow this continued fraction. You take random real numbers with several thousand digits, take continued fraction, and then it gives a big element in SL2Z or in gamma 02, and you consider its representation, calculate this singular values and get the limit. And but really to get, I think 7 digits, it's really the best you can get in this world, because the time grows exponentially. Okay, so get these numbers. I just want to explain a couple of things here. First of all, I put the assumption that spectrum of monodromy around each puncture is.
So you didn't say it doesn't depend on the choice of the method.
No, I will explain it in a second. Yeah. First of all, the assumption that eigenvalues are in U1, it's really necessary for whole thing to have a limit. Otherwise, in oscillated theorem, you get some condition that this one cycle should be, logarithm of one cycle will be some L1 in L1 space on your measure space. And if this condition doesn't satisfy, this L1 condition fails. And in real life, you see that we see no limit. So this thing will oscillate in some interval, this logarithm of critical values divided by t, and there's no limit. The independence on the choice of scalar product is essentially obvious, but why it doesn't depend on choice of Kähler metric? And it's kind of basic effect of conformal of random walk and random motion 2 dimensions. It's conformal invariant if you allow reparameterization of your random walk, or in other words, you say that you consider locally functions which are martingales. These are harmonic functions, and they're harmonic for all these metrics. The satisfied equation depends on a complex structure. Yeah, and that's really pretty nice part of the story. And for example, here I can, in this use of Belly's theorem, you can remove different sets of points. And you get different counters, you get different representation of SL2Z, say, of different ranks. And the claim that the Lyapunov exponents will coincide, I think it's impossible to prove purely in group theory language using this continuous fraction without using conformal invariance. Yeah, so it's pretty nice rigidity of these numbers. And there was a very simple fact that when in all the situation you get numbers whose sum is equal to 0. Why sum is equal to 0? The sum is Lyapunov, the only one Lyapunov exponent of rank 1 local system, which is determinant of my local system. And here the vanishing follows from usual additive ergodic theorem and the fact that random walk is symmetric. So you gain the same going in positive and negative direction, but these things cancel. Yeah, so you don't have really to do any calculation to see this. Okay. Yeah, so it was the simplest setup. And what is the natural generalization of this argument that it doesn't depend on choice of Kähler metric? One can replace curve by a high-dimensional complex manifold. Yeah, so this complex manifold will be, say, dimension n. And also one have to choose a distribution of b degree n minus 1 n minus 1, which is closed and positive as a distribution. So the positivity means that if you multiply by, let's say, C infinity smooth 1-1 form, which is non-negative everywhere, and integrate, you get positive non-negative number. So it chooses arbitrary alpha, and this special case of curve is when manifold is a curve, then alpha will be just function equal to 1. Okay. And now I can see the manifold with this current and also flat bundle with flat connection. And one should put some L1 conditions on both things, on form and manifold and connection to infinity. And then we get Lyapunov exponents. There are separate conditions on current and separate.
Device, you don't want to have just device, you want this current.
Sorry?
Just device, you don't like to have a divisor, you really want this current.
No, it's not divisor. So the first example will be, suppose you get a curve in your manifold, yeah, and you consider delta form of this manifold will be example of this curve. It's kind of linear combination of curves.
Linear.
Yeah, it's not a divisor. It's n minus 1. It's
n minus 1 and minus 1.
Yeah, it's not 1-1. Yeah.
Yeah,
it's really kind of positive linear combination of curves.
Wow, combination.
Yeah. So what is the procedure? So you pick arbitrary C infinity density, positive, strictly positive everywhere, with total integral 1, so it will be probability measure on my space. And now we write a generator of the random walk. So it will be infinitesimal, it will be some kind of Laplace operator. But with degenerate symbol, it will be a Laplace operator only in 2 real directions. No, it could be very degenerate. Yeah, it could be. Of course, it could be just usual random walk on Kähler manifold if it's power of Kähler form. So what's the definition? Take dd bar of the function, multiply by this current, divide by volume element, and you get operator. And of course, it's not C infinity in general because current it's very singular.
You have to say surface and you take bunch of curves there, so you go along curves on them.
Yeah, you go only along curves.
Only long curves.
Yeah, no, but also you can go walk on the surfaces itself. If alpha is powers of Kähler form, n minus first power of Kähler form, that will be usual random walk on a Kähler manifold. So it could be random walk along foliation or random walk along on a manifold as well. Yeah, so one needs the condition that it's really random walk will not go in finite time to the infinity. So it's a special condition for alpha. And also you need, I don't know them precisely, the condition for oscillated theorem to be applied for monodromy should be kind of unipotent at infinity. And then again, you apply multiplicative ergodic theorem, and then you can see that the choice of this measure mu is irrelevant. So you get the same numbers. So essentially by the same reason. I want to say something about this more general framework. In usual, oscillated theorem is applied to station when you get ergodic dynamical system. And here, in this generality, I can have, for example, several disjoint curves, and I work on either of them. So it will be not ergodic. So it will be kind of very easy generalization of Lyapunov exponents to non-ergodic case. Is the following. Actually, it's much simpler than multiplicative ergodic theorem. To give definitions, you don't need anything. Suppose you get a probability space. So you get measure space, and integral of mu is equal to 1. And you get an automorphism. I'll speak about discrete time dynamical system. I get an automorphism, and also I get a T equivariant measurable vector bundle. Actually, vector bundle could be defined over not necessarily complex, could be over non-Archimedean field, any normed field. And what I need a norm on this bundle. And this L1 condition is the following. If you consider function x goes to norm logarithm of norm of the operator ex to e tx, or ex goes to e t inverse to x, this will be, for each point you get operator between two, say, Banach spaces, and consider logarithm of norm. Then should be L1 function. And under this condition, one can define what is a leading Lyapunov exponent. Namely, you consider limit when n goes to infinity, 1 over n, and you integrate over point of your space, mu of x. And now I consider logarithm of norm of the operator acting from e of x, and you compose to e of t to power nx. You compose it many times. Again, you get something in L1. And then this integral, before dividing by n, will be obviously semi-additive function. And because it's semi-additive, and then immediately you see that the limit exists. Yeah, so this, then we define what is a lambda 1 in complete generality, and if my system is not ergodic, it's kind of a family of ergodic system over some base. And then it will be averaged Lyapunov exponent for all this family. But this definition really means it's completely cheap, it doesn't need anything. And if you want to define what are high Lyapunov exponents, you go to exterior power of your representation. So immediately you can define all of them. And yeah, so that's all pretty simple. Yeah, so so there's a special case. Now I return to this case of local system of a complex curve, when my vector bundle with the connection is a variation of polarized complex Hodge structures, maybe not even real Hodge structures, of weight 1. What does it mean? First, it means that the monodromy group lies in a pseudo-unitary group. It preserves some Hermitian form of signature AB. And there will be holomorphic subbundle, which is not preserved by connection, E10 such that if you restrict to the Hermitian form on this subbundle, you get of rank A, you get a positive Hermitian form. So such things come from, it's a bit more general than usual like variation of integral Hodge structure, which come from families of abelian varieties. But it's essentially the same thing. In this case, you get A plus B numbers, and A will be positive and B will be negative. The total sum is 0, as I explained. And the theorem, which kind of in some form I proposed in '96, but rigorously was proven later by Giovanni Forni, that the sum of positive, say, Lyapunov exponents, or minus sum of negative, it will be the same, is twice the integral of first Chern form representing first Chern class of this Hermitian bundle E10. It has carries
It's the curve of the curve.
Of the curve, yeah.
This over the curve.
Yeah. This can be generalized in to more general setting when you get these currents. In a sense, you put here alpha to this integral. That's it. Yeah, so this E10 is Hermitian, it's holomorphic bundle endowed with Hermitian metric, so it has absolutely canonical Hermitian connection and form. Yeah, so that's a formula. And what's the basic idea of the proof? Yeah, so when it arose first, it was appeared in the case when monodromy is symplectic, like for abelian variety. And in this case, if you want to calculate the sum of positive Lyapunov exponents, it's the same as to calculate the growth of the volume of, let's say, real Lagrangian subspace under monodromy. And under monodromy, if you move and you put induced metric and see how the volume grows. And the basic observation is the following. If you consider just usual Hermitian vector space containing, as a real vector space, it's symplectic vector space also. And then we can speak about Lagrangian subspaces. And the claim is the following. So if you consider logarithm of, consider some basis of a Lagrangian subspace, you consider logarithm of the square of norm of this determinant. You can calculate it as a difference of two logarithms in the following way. You choose arbitrary holomorphic volume form, kind of top degree form on this vector space. It will be complex valued form. Take Berenguer complex numbers, consider logarithm of the square, and calculate logarithm of square of this thing. Okay, it's up to some constants, something like logarithm of 2 multiplied by something. And one doesn't have to calculate anything here because by invariance of the whole story under symplectic group, we get homogeneous space. These things should coincide. They have no right to not coincide. And then what follows from this formula, then when you calculate this logarithm of norm and our sum of Lyapunov exponent, its average growth of this number, it will be one expression which is really holomorphic plus anti-holomorphic, and plus something if you choose omega is 0. It's harmonic, which doesn't depend on the Lagrangian space. So if you jump a little bit in all directions in your random walk on a point on a curve, on average of a circle, the increase of the volume will not depend on the choice of Lagrangian. And then you get this kind of nice conservation law. So if you replace random walks by sequence of small jumps distributed around circles, then you get this nice growth. So it was essentially the proof. Yeah, but why, in fact, I started to think about all this stuff? Yeah, and it was really a long time ago. So all the story has now kind of two different applications. One is what's original motivation. It's come from something called Müller dynamics. In this case, this manifold which I consider, it's not a curve in general. It's high-dimensional complex manifold. It's moduli space of quadratic differentials on with given multiplicities of zeros. So some high-dimensional varieties, and then it's foliated by complex curves. Essentially, this some modification. This is some SL2R action, and orbits are holomorphic. The action is not holomorphic, but orbits are holomorphic, and there is transversal measure. So you get really family of curves depending with some transversal measure, and it gives us n-1, n-1 current. Yeah, and around 94, 95, my friend and collaborator Anton Zorich, he discovered on computer experiments some bizarre exponent, which we later realized it's Lyapunov exponent, which was 1/3. And these days people found some really simple reformulation. It was for genus 2 surfaces with maybe quadratic differentials 1, 0, something like this. Suppose on a plane you put obstacles which are rectangles of arbitrary ratio of sides, and you put in a regular kind of periodic fashion. And you now consider a particle which bumps on the boundary of this obstacle, so the directions of the speed will be only 2 directions up to sign. And then if you put parameters randomly, so this particle will kind of move or looks like randomly, but
Parameters meaning
sizes, yeah, ratios on directions, yeah, you choose it at random with Lebesgue measure. And the surprising effect that the distance from the original point, when time is very large, grows not like square root, like you imagine, like random walk, but third root of time.
But for random configuration, just being bound, I guess, yeah?
No, it's on a plane. It's
And
just
on the plane, if you take the position on random, it goes even slower, I think, yeah?
no. I think it will be square root. For random, it will be square root.
No, I think it's just
I don't know.
square root.
No, I think it's like random walk here. It will be.
No, I think it's much slower.
I don't know. No, I don't know.
You take random position, put them in random.
Each of them in random position.
Random medium, I think it's conjecturally bounded.
I don't know, in fact, yeah. No, but here it's a really bizarre exponent 1/3. And then he discovered exactly something like 5 digits, 0.333333. And then it took some time to figure out what is the reason for this, because first we reinterpreted Lyapunov exponent for Müller geodesic flow, but then I got this idea about this identity, which I explained before, and replacing by works. Yeah, but it took something like 10 years to figure out, to fill out the details. Even this 1/3 was proven maybe something like 5 years ago rigorously. Yeah, but then it became kind of quite a popular subject in dynamical systems. So there are plenty of modular spaces here and plenty of bizarre numbers. Actually, maybe I can say some small example of strange thing coming from all these considerations, which is again 2 ways to calculate the sum of Lyapunov exponents of certain identities lead to the following theorem. It's based on many results. Consider symmetric group with n generators for arbitrary n, and consider a set of all pairs of permutations A and B such that A and B generate transitive action on an element set. And commutator has orbit structure, one orbit of period 9 and all many n-9 fixed points. Yeah, in fact, there are about 20 cases. It's the most complicated case of certain results. Yeah, consider this set. It's a finite set.
So it's almost everywhere commute?
Yeah, it's almost everywhere commute. And
except for single.
Yeah, single orbit, yeah. And then there is a free group with two generator acts on the set. Namely, A, B goes to AB times B, or A goes to AB. It's automorphism of free group which acts on the set. You can consider any orbit. And the theorem is the following. The average value of certain function of this orbit, which is in fact functional on one permutation, which is lambda, you consider for each permutation can associate the following rational number, sum over inverse to length of orbits of cycles of permutation. There's some strange rational number. And the average value is belongs to I forgot, something like 33 over 27, 34 over 27, some sort of number. This is a very bizarre. No, you consider any orbit of a free group on this set. Nobody knows what are orbits. One can calculate in computers. There are plenty of orbits, but there are big and small orbits, and for each orbit, the average value of this bizarre function is some specific constant.
For every orbit.
For every orbit, yeah.
The same relation.
Yeah, for arbitrary size, yeah. Yeah, this follows from the proof. It's pretty complicated stuff. It follows from some very nice result by Martin Möller and one of his students about concerning model space of one of this model space of quadratic differentials, some algebra geometric identity in Picard group, and then we should use a lot of use formula, which also Jean-Michel knows a lot about, logarithm of determinants, but for flat surfaces, and eventually it gives us combinatorial, a nice combinatorial statement at the very end. Yeah, so it's.
So you start with these two generators, and how you construct another action? So out of these two generators, you have a new action, yeah?
No, for any pairs of elements, you construct another pair of elements. The commutant will have the same conjugacy class. So this condition will be satisfied. So on the set, the section of free group here.
Okay, given this condition, take action of the free group.
Right? Yeah. And this is the last example. If you consider more complicated conjugacy classes, all this universality will be lost. Yes. Okay, that's one example, but somehow it's really this domain in dynamical systems was closed, and it was not really related to anything else. But last year, Martin Möller figured out one application of this idea to kind of mainstream mathematics, which is the following one. About something like 30 years ago, Delin and Mostov found many examples of non-arithmetic subgroups of finite volume and SU21. These non-arithmetic lattices, which came from monodromies of certain hypergeometric equations. And for this it will be finite list, and for some of these groups, it wasn't clear whether commensurable or not. They defined of some number field. One considered races belongs to the same field, but who knows? Maybe they have subgroup of finite index which are the same. And Martin Möller succeeded to separate all cases, all the things which are expected to be different. He proved they are different. And how he proved? It was the first time this thing was in really not curves, but really high dimensional random walk, he considers ball quotient, and then tautologically this representation, you get a representation group in SE21, which lies in some number field. And Lyapunov exponent of this guy is number 1. It's completely trivial for any lattice in a SU group. Lyapunov exponent is 1. But now, because it's number field, you can embed it in complex numbers in different way. And when you embed it in different way, you get different Lyapunov exponents, which are invariant under commensurability. And calculated in 2 cases, it was something like 5/17 was Lyapunov exponent for one guy and not equal to 7 on 22. And that proves that these things are really different. Yeah, so it's some kind of nice extra invariant in arithmetic groups.
But this again, it's not exactly your situation. It's not, there's no Riemann surface anymore.
No Riemann surfaces, yeah, but still it's the manifold is ball quotient.
Yeah.
And you consider random walk on a ball.
Okay.
With usual standard Kähler metric, yeah.
Usual random walk.
Yeah. Yeah, so it was application really besides the curves in a sense, yeah. It was
Your current is just your Kähler form.
Kähler form, yeah.
Kähler form.
Yeah. Okay, now I'll speak about some new observation which came last fall. So Martin Möller and Anton Zoris, they visited me at IHES, and then Möller suggested why we can always consider variation of hot structure of weight 1. His application was also weight 1 variation of hot structure. And there are, for example, there are families of Calabi-Yau threefolds or whatever, for example, weight 3. It also carries symplectic form. And then one can look on examples of variation of hot structure of weight 3, or CP1 minus 3 points. So one get monodromy, should get 2 monodromy matrices, the rest with the product. And there is a natural class of this monodromy matrices, which right here, it's exponent of lower diagonal unipotent matrix. And such operator, yeah, for those who know, I can say that it's, the things were known from mirror symmetry. One corresponds to action on cohomology of threefold by multiplication of a first chain class of ample line bundle. And this is reflection with respect to spherical object with sheaf O. So it's things were known for different reasons. But okay, now I ask that the product will have eigenvalues on the unit circle, so 2 numbers between, and I normalize, you get 4 numbers, but because of rarity and symmetry, you get only 2 numbers. And normalize, I have 2 parameters. So what I denote by star, it's uniquely returned by these 2 parameters. So the parameter space is a triangle. Alpha 1 is less than alpha 2. And in the claim that inside this triangle, there's 1/3 of this triangle given by some inequality, which I don't understand the origin of, but it's kind of numerically checked, so it's very clean that it's right inequality. And then the sum of Lyapunov exponents is again equal to twice the first Chern class. But of what? I now have variation of hot structure of weight 3, so it has 4 components, E30, E21, E12, and E03, each of them 1-dimensional, 4-dimensional space. And I take a term of middle term of Hodge filtration, get 2-dimensional bundle, and it will be exactly degree of first Chern class. Yeah, and if this inequality does satisfy, then my equality will be broken. The sum of Lyapunov exponents will be larger. Yeah. So initially, when I started computer experiments, I look on algebraic cases, which correspond to variation of host structure, mirror rule to complete intersections of Calabi-Yau threefold in some weighted projective space. One can find the tables in the literature. There are 14 different equations. And these 14 cases are distributed in 7 good cases when I get equality, and 7 bad cases when I do not get equality. So, and case of mirror to quintic, which I'll explain in a few minutes, is one of good cases. And it was a very remarkable coincidence because also in the fall, Peter Sarnak started to talk about thin groups. What does it mean? So there's a question which I found a bit strange. If you consider monodromy representation of fundamental group over some algebraic variety in some Gauss, in some Picard-Fuchs equation, you get a subgroup which is whose Zariski closure is some reductive group over defined over rational numbers. And the question, is it arithmetic group or not? Or no, not arithmetic. It could have finite index. Is it finite index or not? Of course, I do expect it should have infinite index in general. But somehow it turns out that people were not able to prove it till very recently, till again last fall. And somebody really working on for stability and mirror symmetry.
What kind of groups again?
Image of fundamental group of algebraic variety in monodromy representation. If you get some family varieties of some base. Yeah, in general, I would expect it to be the risky closure. It's big, but the group itself should have infinite index. Yeah, and people found finally example when have infinite index. It's called thin groups, and exactly studied these 14 cases.
Infinite index in which group?
In the risky closure in arithmetic group. It's in
The Zariski closure is just
big SLNZ, yeah.
it's infinite group.
Of course,
You're
infinite.
doing continuum group.
No. I mean integer points in the.
Integer points.
Yeah,
Okay.
of course, it's
Integer
integer point. Yeah, and yeah, I was even surprised that there are arithmetic cases here, and exactly bad cases, which are 7 bad cases, correspond to arithmetic situation, and good cases, when I get exact formula, correspond to this thin group, which kind of should be generic situation. Yeah, in fact, I don't think it's really coincidence. It's there should be something in the argument which shows that some Lyapunov exponents is what I need.
How thin?
No, they're really.
How you?
No, I think it's much small. I don't know, much smaller. Yeah. No, definitely. No, if you look, I actually don't understand what's the equation, because if you look on the computer, start to multiply these matrices, you see that immediately the coefficients grow so fast. There's really no way to go back to normal size matrices. So it's
for example, homologically, how much the homological dimension?
no, that's exactly, yeah. They prove that it's embedding. No, homological dimension is 1, and homological dimension of ambient group will be 2, for example, here, or 3.
So they have small dimension.
Small homological dimension, yeah. Yeah, so one can try to repeat the arguments which have for weight 1, but then it starts to, if you look on this, it breaks down. Where it breaks down. You start to move Lagrangian manifold, and you consider this holomorphic subspace of middle dimension, and you do this volume form. But opposite to the situation of Hodge structure of weight 1, it's quite possible that real Lagrangian subspace will be not transversal to the middle term of Hodge filtration, because the signature is no longer positive. And then a break situation. And then what is the heuristic? What goes on? First, in general, let's consider this 4-dimensional bundles of middle cohomology or some CP1. You consider bundle of Lagrangian Grassmannians, because we're interested in real Lagrangian subspaces. And this bundle of Lagrangian Grassmannians also carries a flat connection. So I get total space will be more or less compact, except the CP1 minus C point is not compact. And it carries a 2-dimensional foliation, so we can lift our random walk to the ambient space. And because it's essentially compact, it should have invariant measure. And invariant measure, it's not nice invariant measure like we have on the base. It's very singular on the fiber. And on the fiber, it's supported on some fractal circle. We don't know if it's continuous, but roughly it should be S1 embedded in some fractal way to the special Lagrangian. And the origin is the following. It's very general for this Lyapunov exponent business, where we get these subspaces, circles in Grassmannian. Why circle? Because when consider, let's say, again, hyperbolic metric, we can replace random walk by geodesic flow. We kind of shot in a random direction. We shot in random direction. And then from infinity, we move our space. And then at half of direction, it will expand, half direction contract. So we get certain subspace in my space depending on the direction. And but depends on direction. Direction it's one angle, so we get a circle embedded to this Grassmannian. In general, one get a circle embedded in a flag variety. It's a circle if we are on a curve. No, curve, because we are on a curve. No, if you are on a ball, then there will be boundary of a ball embedded in Grassmannian. Some kind of boundary of at infinity on a universal cover. Yeah, so you get a circle, and there's really no way to write formula for the circle. And in fact, one gets some bizarre fractal measure on the total space, and Lyapunov exponents one can write as integral of some nice function with respect to this measure. Yeah, so that's why it's difficult to calculate it in exact way. So in general. Okay, so we get this circle, and it looks that's a nice situation when we get exact formula that sum of Lyapunov exponent is what we want. Correspond to very special situation when the support of this measure with this fractal covariantly constant circle, it's also covariantly constant under flat connection, is everywhere on my universal cover transversal to this space in the Hodge filtration. You see that the condition that you get one real Lagrangian space and one complex Lagrangian space. The transversal to be not transversal means some complex determinant from 0. You get some complex number should vanish. So this non-transversality happens in real codimension 2. So it's some isolated points on my universal cover. In general, one expect this non-transversality. And the claim that by some miraculous reason it doesn't happen. Yeah, so this one can check even better than making random walk, this non-transversality. For example, for the quintic case, what we calculating? We calculated, we need some, oh no, it's mirror to quintic, yeah, it's some differential equation correspond to mirror to quintic, yeah. It's, so we get some fourth order differential equation, and we look on solutions, and now we look on, if consider solution of this equation near point 0, yeah, so this equation on CP1 minus 0, infinity instead of 1, this arbitrary scaled 1 over 5 to power 5. So we get this differential equation, it has 4 solutions, and consider the only one solution is non-singular, it's integral of a vanishing cycle, and there is a next solution which associate to it. And the first solution have a logarithm square and so on. So there are explicit formula. Then I calculate Vronsky determinant of these two solutions, get multi-valued function. And the claim this multi-valued function on universal cover never vanishes. That's what says this prediction. It's actually correspond to what points in a circle. I said that there should be whole circle consisting of this nice real two-dimensional subspace which never meet terms of Hodge filtration, which is essentially non-vanishing. And the circle has one very, so we should find at least one kind of specific real two-dimensional subspace in cohomology. And there is a natural candidate near point 0, the monodromy is unipotent, there is this unique invariant subspace by dimension 2. I pick this and expand to these two solutions that is a determinant in the search to them. Yeah, in general, because of universal coverage is action of fundamental group, we get kind of copy of QP1. The monodromy, so you get not only one point, but count remaining points will be everywhere dense, supposedly, on this circle. So we kind of reconstruct the circle directly from this picture. Okay, so we get this function, and it doesn't vanish. Yeah, so I check it with very high precision. So the best, kind of the most convincing formula was the following. You rescale your argument and also multiply by variable z. The non-vanishing will be the same. And now make a change of coordinates using something which is not related to Calabi-Yau's threefold, but usual modular forms, how to cover CP1 minus 3 points by upper half plane. It's some standard modular function from elliptic curves and from Calabi-Yau's. You make the substitution, you get function in a unit disk, and the claim it's not vanishing, or logarithm has no singularities, and this logarithm should have it means that logarithm has radius convergence equal to 1. But in fact, the coefficients are really bounded. And I don't have picture with me, but I can. I remember I tried to plot them. Yes, so that was the most convincing expression here. I calculate maybe several thousand coefficients and Taylor coefficients, and the plot of these coefficients was like this. So it will be kind of constant taking few values. Yeah, essentially, I think it's corresponded, should be some explicit formula for this guy, some product formula. Yeah, so all the thing, it's analog of product of such thing in modular forms, but kind of behave a bit different, because consider logarithm of this and expand, then coefficients grow something like double logarithm. And here get really uniformly bounded. And yeah, it will be pretty interesting to study the mechanics of it. But my guess is actually it's not a deep result. It's not miraculous 6 like a number theory. You get this modular form which is not vanishing everywhere, which pretty unique object. Here I think it's pretty robust situation, because I recall you that in the parameter space, we get the whole open domain of such things. So it's really, we can change parameters, things will be still okay. And I think it's related to the property that this group has seen, because how people prove the group has seen, they prove something called, I don't know, it's ping pong argument. So they're really kind of bound domains when group elements connect. So it should be pretty robust inequality. So it's nothing miraculous in sense here. Okay, so in general, one can analyze the argument and see that it's always related to Calabi-Yau, because when we calculate sum of Lyapunov exponents, it will be leading Lyapunov exponent of exterior power. And we take sum of Lyapunov exponents, the number of Lyapunov exponents will be exactly dimension of terms of Hodge filtration. So it means this is exterior power, the lowest term of Hodge filtration will be one-dimensional. Yeah, so it's, and the whole argument, it's really a kind of variation of Calabi-Yau Hodge structures. Suppose I get a variation, let's say, of a curve. Of course, it can be generalized to this currents. Have a variation of Hodge structure. Let's say it's irreducible, and let's say dual variation is Calabi-Yau, so it has the lowest term of line bundle sitting nice way inside this variation. And assume that we have a flat multi-valued section of my local system on universal cover, and such that it pairs with this line bundle non-zero everywhere. Then heuristically, one can expect the leading Lyapunov exponent should be integral given by first chain class, because this line bundle will provide a norm on the section, non-vanishing everywhere. But here, I think the analytic difficulties will be pretty heavy, because one kind of should integrate by parts in a sense, and boundary terms, what is L1 on L1, it will be formally it works, but analytically, I think it will be some difficulty to really make it rigorous. Yeah. So maybe before going on, I just want to say a few things about this viewpoint. First, I explained that I have weight 3, and all Hodge numbers equal to 1. I get sum of two Lyapunov exponents is equal to over Riemann surface. Yeah, I have these examples of Riemann surface. Sum of Lyapunov exponent to 1. But then the same is Lie Lyapunov exponent of exterior square, and one can take primitive part of exterior square. This is symplectic vector space, so it's 5-dimensional space, and Hodge numbers 1, 1, 1, 1. So it looks like weight 4 variation of Calabi structures of weight 4. And here we get just leading Lyapunov exponent. Also, I tried a few other cases. I have this quintic case, but one can consider replace 5 by arbitrary integer. You get the integer d, you get a d minus 1-dimensional local system. And I think I take almost half the wedge power of this integral system. Then lambda 1 of this thing is again as expected. It's in fact some half integer. I forgot exact formula. So I checked it for d equals 6 and 7. It also works. Yeah. So it seems that the story is not bounded to any specific weight. And so now one can ask also the following question. There was in the original case when we started with variation of Hodge structure of weight 1. There's really no miracle that things is not vanishing, because it wasn't vanishing this pairing between section and terms of Hodge filtration by purely theoretic reasons. We have symplectic vector space, and so the story is that if we have a real symplectic vector space, and if we take any real subspace, a Lagrangian subspace, and any Hermitian norm which gives complex subspace, then it will be always transversal. And in general, one can ask what properties of Hodge structure will guarantee this for free. If you get a variation of Hodge structure, then you get, for generic point on the base, you get some Mumford-Tate group, some kind of like the Riski envelope of a fundamental group, or actual fundamental group, and it's encoded in Lie theoretic language in the following way. So first, suppose you have a compact Lie group. You have its complexification, and to relate it with Hodge theory, you should map a circle or double cover of standard T1 to the compact group, such that element in the double cover, which is square root of 1, will go to a central element. Then any representation of this group will carry naturally a Hodge structure. When you complexifies the Lie algebra of a compact group, or any complex representation will have, because action of this U1, and it will be kind of P minus Q over 2 in HPQ decomposition. Okay, in particular, Lie algebra by a joint representation is Z-graded on the classification, and if you consider Lie algebra of compact group, it's just split in even an odd part, responding to this parity of the grading. And now I can consider another real subalgebra in a complex Lie algebra. You multiply by I the odd part, and you get a real form of the group, some non-compact real form. And the equation, one can formulate the equation of this non-vanishing to the following: does there exist a representation, finite-dimensional representation of this compact group or complex reductive group, and the highest vector with respect to should be highest eigenvalue of this U1 acting on this thing, but it will be typically just the highest vector for the canonical Borel group. Such that, and a vector in dual representation, a vector in my representation, such that to consider real orbit of my group, it will be never orthogonal to this complex vector. Yeah, so it looks it's a simple question, but the original example was when the group was unitary group, compact form symplectic group, real form it's usual symplectic matrices, and representation was primitive part of wedge product of this non-vanishing happens here, and but there are other examples not coming from abelian varieties, for example, coming from Shimura varieties of exceptional types which cannot be reduced to symplectic group. And here we also get some of Lyapunov exponents, and this equation which I can just raise if you're interested to find other examples when we can have this robust mechanism which can be applied to this Lyapunov exponent business.